So my lab studies this microendemic radiation of pupfishes found only on this tiny island of San Salvador in the Bahamas, despite an abundance of similar habitats throughout the Caribbean. So here's the range of pupfish shown here in blue. They range all the way up here to Rhode Island, back down to Venezuela. And we have an endemic scale-eating pupfish. So shown here, it actually bites the scales off of other fish. So this is like me coming up to you, biting off your fingernails before you run away. 50% of their diet is scales. And in the lab, you can see this in slow motion, filmed at about 2,000 frames per second. Look at the spray of scales coming off the side of that fish. So there's other scale-eating specialists out there, but among Cyprinodontiforms, this is the only specialist. There's a second specialist on San Salvador, this molluscivore pupfish, Cyprinodon brontothyroides. And here it has a novel nasal protrusion coming out of the top of its maxilla. This is actually a skeletal protrusion shown here in blue, relative to the massive oral jaws of the scale eater and the sort of generalist morphology here. So we think that this protrusion is actually a stabilizing appendage as it rips the snails right out of their shells. So shown here. And there this empty shell falls away. So when we find just the bodies of snails in their stomachs. Now there's other specialized molluscivores out there with a nasal protrusion, like this drum found off the coast of South Africa. But again, this is the only specialist within Cyprinodontiforms with this novel trait. Now, 6 years ago, I presented at this conference that multiple fitness peaks are driving adaptive radiation in this system. So here I'm showing you this fitness landscape estimated from F2 hybrid survival on San Salvador Island in field enclosures. And this is in 2 dimensions and 3 dimensions. And so this is basically a discriminant analysis, so maximizes phenotypic discrimination among the 3 parental species. So here's the molluscivore, shown here on the bottom left, generalist here, and scale eater here. So these are 95% confidence ellipses. And these hybrids that I actually placed in the field enclosure are each of these points. So it's about 900 hybrids, the survivors and the deaths in gray. And then we can fit a thin plate spline to these survival data to actually estimate the fitness landscape. And you can see it's incredibly complex, with a high fitness peak corresponding to the molluscivore, a small fitness valley here, and then a local fitness peak isolating that generalist phenotype. Whereas the scale eater phenotypes, the hybrids that look like scale eaters, do terrible, right? And this provides a potential unexpected explanation for the rarity of adaptive radiation across the Caribbean. So this is a classic problem on fitness landscapes, is that these generalist populations might be isolated on a local fitness peak across all these there's lots of other salt lakes, they only have generalists. And I manipulated density in this first experiment. So showing that with higher densities here than low density enclosures, the fitness landscape is more curved. So competition is driving increased multiple fitness peaks in this system. And I should stop right there. Right? This is all consistent with what we expect. Ecological opportunity provides these multiple fitness landscapes, right? But when we look at this, rare phenotypes here at the edges of this morphospace do not show a fitness advantage. Right? These guys are rare, they're doing fantastic. These guys over here are doing terribly, and these scale eaters are rare. At least some of these things should be doing well. And if we look at residual survival here, plotted against the sort of density of phenotypes, similar phenotypes, so the 10 nearest neighbors in phenotype space, at first they start to do better, which is what we expect, as they have fewer competitors. But as the phenotypes become more and more rare, their survival plummets. And this is replicated across 2 different high-density lake enclosures. So rare phenotypes do not show a fitness advantage. But theory says rare phenotypes should have a fitness advantage. Right? So negative frequency-dependent disruptive selection is sort of the foundation of many of our speciation models today. So Dyckman and Dobelli, right, this phenotype drifts is selected for towards this middle of this distribution, but then these rare phenotypes have an advantage. That disruptive selection actually splits the population. So this is what's driving speciation models. This is what we expect for experiments. There's lots of experimental evidence that rare phenotypes should have this advantage. Um, so the talk today is about sort of what factors shape the fitness landscape. Is it the relative frequency of competitors? So we can think of a trampoline. So as we have more competitors, it depresses the surface of that trampoline. Or is it the absolute performance of these phenotypes, regardless of the number of competitors? So this is more of a sort of mountain range metaphor, where you have static fitness peaks due to some stable performance optimum. So, you know what they say, never repeat a good experiment. But I did. So this is my postdoc experiment several years ago now, this time with over 4,000 F4, F5 hybrids. I thin clipped them all so I could later genotype them. That's another talk. Frequency manipulation this time. So I actually selected for the rare phenotypes. So here it is. This is in my tiny little fish room at Berkeley. There's over, there's almost 1,000 fish in this one little tank. So all these dots here are fry in one bucket. And first problem. So 1, 2, 3, 4 crates, each with over 1,000 F4, F hybrids were packed. Took about 8 hours, 3 crates here. So 1 crate never made it to San Salvador. It's still stuck at SFO somewhere, never to be found. I still managed to tag over 3,000 hybrids. So these are coded wire tags that we use. And then took individual photographs of left, right, and dorsal sides of each hybrid. Built these field enclosures in the wild again. So here's one lake, these two, and then the second lake, a low frequency and high frequency enclosure. Where I ended up having to select basically by eye for more rare phenotypes in one and sort of everything generalist in the other. And finally, this is the moment of truth, reintroducing these hybrids to the same lake from which their great-great-grandparents were originally collected many, many years earlier. So I went home, right? Second problem. Hurricane Cristobal, my namesake, veers around. This is San Salvador. I hop on a plane as this hurricane is barreling towards San Salvador. At the last minute, it veers away from the island. So I show up, enclosures are pretty much fine. There's some chop. And I harvest. It's been 3 months. Third problem, 77% survival in that first set of enclosures over 3 months. Even though the first time I did this, it was 10% survival. When you do a fitness experiment, you do not want this much survival. That's bad. So I left the other set of enclosures out there for a year. I was pissed off. And I come back in April 2015 after they've been out there for a year. This is my perplexed face that they're even still there. Fourth problem, 1% survival. But look at this pattern of survivors. So when I first looked at this fitness landscape in the second lake, it's beautiful, right? There's 2 isolated fitness peaks. Fifth problem, undergrad measurements. So it turns out that I had personally measured, of course, all the survivors, and I had undergrads measuring the deaths. But that actually inflates the variance around these peaks, around here. So then I realized this and went back, and so personally rechecked all these measurements with image J. So it's 30 linear distances and angles measured on the left, right, and dorsal surfaces. So finally, this is the final data set. It's almost 3,000 hybrids measured for 30 traits and angles. So on the top row here is Lake 1. So high frequency here, low frequency here, and then control hybrids that were raised in the lab for the full year. And I just tracked when they died. And here's the second lake on the bottom row. High frequency, low frequency, and then again for reference, molluscivores on the left, generalists, scale eaters. And again, in the second lake, the molluscivores have a more pronounced nose. So essentially the y-axis here is, as it goes down, it's increasing nose size. And on the x-axis, it's basically increasing jaw size. So we can fit thin plate splines to these data. And this is the sort of survival fitness landscapes that I've measured on the second experiment. And we can see in the first lake, there's basically, so increasing survival in red here. There's basically strong directional selection on the generalists here in the middle. You can't quite see, so hybrids resembling the generalists in both high and low frequency. And then in the second lake, there's strong stabilizing, disruptive, whatever you want to call this, on the molluscivore phenotypes. But this is quite strong. So survival probability is going from 0 to 80% here. Pretty dramatic survival where all of these survivors, even though it's very few, they're basically in this area of that morphospace. And then if we look at the controls, so these are just fed pellet food in the control. And actually what I originally expected with doing the first experiment. The scale eaters here on the right side, these reddish ellipses here, scale eater type hybrids do better in the lab because they're aggressive. They get all the food. And one more thing I want to point out here, there's basically no difference between high and low frequency in these landscapes. And I would say basically the same in this second lake. And so using general additive modeling, I've compared these two different models. There's no effect of treatment on the shape of these landscapes. And we can look at another cross-section through this sort of 30-dimensional fitness space. So this is using projection pursuit regression, where we can pull out the two axes of selection, are basically two axes in this phenotype space that are most curved. So the most interesting selection axes. So in this slice, it actually has nothing to do, all the parents are clustered on top of each other. It's basically saying that the rarer your phenotype is, the more distant it is from those three parental phenotypes, the worse you do. So rare phenotypes here are doing very poorly relative to the parentals. And again, we sort of see all of these sort of parental type hybrids clustered on top of each other, and the sort of weirder you look, the worse they're doing. And similarly, within an enclosure, we can look at the frequency of competitors, right? And this should be going up if rare phenotypes have an advantage. There's basically no relationship here. This is overfitting, but essentially there's no effect of the density of similar phenotypes on your own fitness within these enclosures. And again, I've modeled this with general additive modeling, which I won't go into here, to sort of formally test this. So, summary here is that rare phenotypes fare poorly. There's no evidence that I can find of frequency-dependent selection on survival. I did find a strong effect on growth weight, which I won't present here. But here's what's really fascinating. Because there's no difference between these different treatments, we can actually combine our estimate into a single fitness landscape. So if we combine the low and high frequency treatments across lakes, we can get one fitness landscape for all 4 treatments. And it's beautiful, right? So essentially what's happening here is we get an isolated generalist fitness peak, a small fitness valley, and a higher fitness peak corresponding to the molluscan form. So very similar to the first time I did this, just that this is spread across lakes. So strong selection for generalists in one lake, strong selection for molluscivores in the other lake. But then when I looked at growth rates, it's actually similar to different fitness peaks. So here, generalists on an isolated fitness peak for survival. Here, sort of generalist, this is the isolated fitness peak for growth rate. And I won't go into this too much, but we can look at all fitness trajectories in this trait space and plot a survival spine. And the striking thing here is that I basically oriented these axes with a discriminant analysis. So here's generalists, here's scale eaters across all 4 enclosures. And right here, fitness declines as you head towards scale eaters. In all of these except here where we're missing some data. So there's a stable scale eater fitness minimum across all trait sets. So multi-peak fitness landscape is surprisingly consistent across experiments, fitness proxies. And the most stable part of this is the scale eater fitness valley across lakes, experiments, frequencies of competitors, and time periods. So this suggests this sort of absolute performance of phenotypes is shaping the fitness landscape, not just the frequency of competitors. And this makes sense when we think about the performance demands of these 2 niches, right? Scale eaters are doing high-speed strikes in 15 milliseconds, getting very low caloric payoff per strike. And my grad student Joe presented yesterday on intrinsic genetic incompatibilities in this system. I'll cut it off there. So potentially large and stable fitness valley. But if you think that introgression might play a role, go see my grad student Emily's talk tomorrow.